Okay, so last time we already discussed about the shift of TTT curves, right? With adding alloying elements. Okay, and this alloying elements will causes the shifting of the TTT curve. So what's the physical meaning? Uh, so what's the physical meaning of this shifting? So that means the martensite is easy to form, right? The martensite is easier to form. Why? Because, for example, I just draw another CCT curve. Okay, another CCT curve like this. Sorry. So this temperature should be higher than TE. Okay. Therefore, I have two CCT curve continuous cooling. Okay, continuous cooling. So this is curve 1 and 2. Okay, 1 and 2. Okay. So for the curve 1, CCT curve 1, for the TTT curve 8, what's the structure should be formed for the CCT curve 1? This is CCT, continuous cooling transformation. For the CCT1, the martensite should form, right? Because there's no intercept of the TTT curve 1 and the curve 8, the TTT diagram of 8, right? Okay, and for the CCT curve 2, the blue one, the blue curve, for the TTT curve 8, so what's the structure should be formed, right? You can look at this curve 8. It shows that there's two intercepts of the curve 8. One's here, and the other one's here. Okay, so what's that mean? That means the CCT curve 2 what began to transfer from the austenite to pearlite structure, right? You know what I'm saying? So the austenite begins to transfer to pearlite structure at this moment, and the 100% of pearlite form at this moment. Okay. Okay, you know what I'm saying? So it's transformation process. Okay, if some alloying element added in this steels, the TTT curves will shift from A to B. So what's that mean? That means the CCT curve 2 will make the structure what? So what kind of structure will form if this TTT curve shift from A to B with the CCT curve 2? The martensite structure will form, right? Why? Because the curve A shift to B, from A shift to B, right? And for this blue curve, for the blue curve, there's no contact with the nose of curve B, right? There's no contact, right? So there's a distance right here. What's that mean? That means the austenite, that means the pearlite will not form during this cooling process. Okay, or we can say the austenite didn't transform to pearlite. Okay, it will transform to martensite directly. Right, you know what I'm saying? So you can see the curve 2, the blue one, and without any contact with the nose. Right, that's mean the martensite will form directly without any transformation of pearlite. Okay, Okay, so for this one is the alloy steel. Okay, so we're just adding other alloy elements to shift the TTT curve and make the margin side easier to form. Okay, and the composition of austenites to ferrite is the light. Okay, so that's the one process to harden this kind of steel. Okay, and the other process is called the participation precipitate hardening. Okay, precipitate hardening. So for the non-ferrous or stainless steels, so what's the process of precipitation hardening? That means some particles, or we can say that dispersed phase, form to impede dislocations, right? For example, aluminum copper system. Okay, so let's focus on this binary phase diagram. It's copper and the aluminum phase diagram. Okay, and let's draw let's plot the figure of temperature versus time. Okay, what we get. Okay, initially the particle 8 solution heat treat to get alpha solid solution, right, at 0.8. Okay, at 0.8. Okay, at 0.8. Right? We heat up the temperature to specific temperature for the solid solution to get the solid solution. Okay. And for point B, just change to room temperature, right? We heat up at the specific temperature. For in this case, it's about like 520 Celsius to form the alpha solid solution. And then change to room temperature. Okay, change to room temperature B. Okay, and reheat it to nucleate small theta crystals within alpha crystals. That means the other phases form, precipitate. Okay, precipitate. The second phase, the second solid phase form in alpha solid solution, right? And this time we call it agent. We call it agent process. Okay, and the temperature control and aging control dominates the precipitation hardening. Okay, and how longer for the aging will modify the alloys hardness or its mechanical properties. Okay. So other precipitation systems such as copper, tin, and so on, magnesium, aluminum, and so on. Okay, so the relation between the strength hardness and the aging time, as I already mentioned in previous slide, it shows that we have the it has the optimum aging time with the highest hardness or mechanical strength. Okay, okay, and when this aging time is longer, to reduce the alloy's hardness or strength, that means it's overaged. That means overaged. Okay, it means overaged. Okay, and so we have to modify our aging process to get the highest hardness or strength. Okay, So we have to find the optimal time for aging. Optimal time for aging. Okay. So it doesn't mean that the longer aging time is better. Okay. So the surface treatment, it often advantageous to have a steel with the hard surface but ductile center. This could be accomplished in multiple ways. Okay, selectively heating the surface, so we can rapidly heat the surface of the medium carbon steel and then trench it, and this result in a hot martensite surface and a softer center of perlite and ferrite. And the depth of the martensite layer is the K steps. Okay, K steps. It depends on your application, how thick of this hardened layer that you want. Okay, and we can also selectively heat the surface by using tempering or selective heat sources. Okay, and the other process to a surface treatment for hardening is carburizing and the nitriding. And these techniques involve a controlled diffusion of carbon and nitride. Okay, for the best toughness, we start with a low carbon steel. In carburizing, carbon is diffused into the steel surface at temperature above A3. So what's the temperature of A3? The temperature A3 is normal. It's the normalizing temperature. Okay, it's the normalizing temperature. And A1 is TE, the eutectoid temperature. See, and when the steel is then trenched and tempered, and the surface becomes a high carbon monazite. Okay, nitrogen provides a similar strength effect to carbon. It can be introduced via various masses and so on. Okay, so let's look at this. This shows the surface treatment. For example, we have a rod or we have a shaft. For shaft, we need very hard surface to improve its anti-wear capability, right? And so we can surface hardening by localized heating. Okay, just heat the surface. Okay, and the heating is only at the surface. Okay, and only the surface heats above A1 temperature and is trenched to martensite. For example, okay, we want this shaft is K steps is certain specific dimension. Okay, and this is what we want for hardening thickness here, and we call it K steps. Okay, K steps. So we have to heat treat by local heating, only the surface heated above the A1 temperature. Okay, therefore this thickness or the depth is called the K steps right here. Okay, so here is the surface. Here is the surface. Okay, and this is the depths. Okay, the depths. Okay, and only the K steps will be heated above A1. Right, this is the A1 right here. Okay, only the K steps here. The thickness of the K steps be heated above A1. Okay, of course, it's the surface, and the side is the surface. Okay, and this is the K steps. K steps. Okay, and for the K steps, you have to hit it above A1. Right? What is A1? It's right here. Right? Above the eutectoid temperature, or we can say the equilibrium temperature. Okay. Okay, and also we can carburizing of a low carbon steel to produce a high carbon to improve its wear resistance. Okay, or the wear resistance surface. Okay. So there's some properties or some for these stainless steels, like stainless steel contain at least 11% of chromium, which forms a protective chromium oxide layer on the surface, giving the steel excellent corrosion resistance. Okay. Okay, but it doesn't mean that it never corroded. Okay, it doesn't mean that it will forever and ever, okay, not to be corroded. Okay. And the ferritic stainless steels have up to 30% of chromium and less than 0.12% of carbon content. Good strength, moderate ductility, and the ferromagnetic, not heat treatable, relatively inexpensive. Okay, therefore, if you wanna, well, you wanna if you wanna need a low cost stainless steel, and we need a moderate ductility with good strength, well, maybe we can use ferritic stainless steel. Okay, and the martensitic stainless steel that contains less than 17% of chromium with the 0.1 to 1% of carbon. Of course, it is a martensite structure, right? Therefore, it has the high hardness, strength, and corrosion resistance that make them useful for knives, ball bearings, valves, and so on. Okay. So it totally depends on where your application is. Okay, you need what kind of the mechanical properties is your priority. Okay, so for example, if this component will be used in a high humid environment, of course we have to focus on its anti-corrosion, right? We have to focus on its corrosion resistance. Okay, and austenitic stainless steels adding nickel makes it possible to have steels with nearly all austenite without ferrite at room temperature, and excellent flammability, ductility, corrosion resistance. Okay, not for magnetic and might be cold work expensive and corrode at high temperature. Okay, therefore, what's the specific property for austenitic stainless steels? Flammability, right? Flammability, ductility, and the corrosion resistance. Well, if your specification application is for the corrosion resistance, well, maybe austenitic stainless steel could be one of the choices. Okay, and precipitation hardening stainless steel, the content aluminum, titanium, and drives properties from aging and the strength hardening, monocytic reaction, and solid solution strengthening. Okay, and high strengths are obtained even with low carbon content. Okay, and the duplex stainless steels, sometimes the mixtures of devices are deliberately introduced in steel to obtain combinations of properties not found in typical steel. Duplex stainless steel contains 50-50 ferrite and austenite. Well, as we know, the austenite structure, it's not 50-50 ferrite and austenite, right? And what is austenite? It's a solid solution, right? It's a solid solution. Okay, and duplex stainless steels contain 50-50 and can be produced via controlling composition and heat treatment. Okay, and most stainless steels are recyclable. Okay, can be recycled. Okay, therefore it's a good materials for environment. Well, it's environmental friendly. Okay. Well, there's some typical composition and properties of stainless steels. So you guys can just look at this table or from your textbook. Okay. And for cast irons are iron carbon silicon alloy. Okay, so there's some small content, less content of the silicon inside cast iron that pass through the eutectic reaction during solidification process. So what is eutectic reaction? What is eutectic reaction? What is eutectic? Eutectic reaction is the transformation from single liquid phase to transfer to what? To solid phase, right? To solid phase. Okay, they typically contain 2 to 4% of carbon and 0.5 to 3% of silicon. And initially, the eutectic reaction produced white cast iron. Wow. So as we heard as the white cast iron, so what you can think of? What you can think of? Well, it's what's the mechanical property of white cast iron. It's very hot, right? Right? Because it's composed of cementite and pearlite structure. However, this is made a stable phase. Okay, and under true equilibrium conditions, the graphite eutectic reaction occurs, and the gray ductile or compact graphite cast iron film. That's we saw initially. Initially, the eutectic reaction produced white cast iron, and gradually, it will transfer to what? To gray cast iron or compact graphite cast iron. Okay, because it's a metastable phase, or we can say it's a transition. Okay, it's a transition formation of a white cast iron. Okay, and silicon is added for its graphite stabilizing properties and to reduce the amount of carbon in the eutectic. Okay, and silicon also encourages the stable eutectoid reaction. Okay, so the previous one is eutectic reaction. Okay, and also the silicon encourages the stable eutectoid reaction. Okay, and annealing of cast iron gives a softer ferrite matrix. Okay, and normalizing gives the palladic matrix. Okay, so which one will produce the a higher hardness? Which one? Of course, normalizing, right? Because for annealing of a cast iron, we get a softer ferrite, right? Soft ferrite. You have to remember that ferrite is always soft, okay? And normalizing process gives a pearlite, okay? Pearlite structure and ferrite. Okay, and great cast iron, most widely used cast iron, contains eutectic cells of interconnected graphite flakes, which cause low strength and ductility, and high compressive strength, machinability, thermal conductivity, vibration damping, and resistance to thermal fatigue and sliding wear. Okay, so you have to specify your applications for great cast irons. Well, if you need a very high conductivity component, it would be a good choice. Okay, so what kind of components that need high thermal conductivity? Engine block, right? Engine block for cylinder, for piston. Okay, we need what's the application of the engine block and what's its property should be for the piston movement. Okay, the engine block needs high thermal conductivity, right? Because when the piston moving, it's a cyclic movement, right? Will produce the very high heat, and it's need to anti-wear of sliding, right? Anti-wear of sliding. Okay. Okay, white cast iron is hard, brittle alloy with high amount of cementite, used for hardness and resistant to abrasive wear. Okay, that's for sure. We already know that. Malleable cast iron formed by heat treatment of white cast iron produces round and clumps of graphite. While graphite formed will reduce its hardness. Okay, okay. The graphite formation will reduce the hardness of white cast iron. Therefore, it's very ductile and machinable and can be produced by heat treating unalloyed 3% carbon iron undergoes 2 stages of graphitization. Okay. Okay, ductile and the nodular cast iron contains spheroidal graphite particle. Once you find this spheroidal or round, this kind of shape, this round shape, its hardness will be reduced. Okay, will be reduced. Okay. Producing requires several steps as desulfurization, neutralizing, and the inoculation. And the ductile cast iron has excellent strength and ductility, stronger than malleable iron, but not as tough. Well, if you need a high toughness of cast iron, maybe it's not a good choice. Okay. So what is toughness? What's the definition of toughness? What's the definition of toughness? That's the ability to, what's the ability to strength, right? That's mean it's the ability for strength energy or the deformability. Okay, so that means the higher toughness, these materials have the higher energy to observe the deformation. Okay, then the compacted graphite cast iron contains rounded. Okay, so you look at these keywords: rounded. Okay, right, rounded, or these kind of spheroidal. Okay, okay. So this compacted graphite cast iron contains rounded but interconnected graphite. This permits strength and ductilities exceeding those of great cast iron, but still allows good thermal conductivity and vibration damping properties. Wow, see, it's kind of a compact grade graphite cast iron has good ductility. While the ductility exceeding those of great cast iron and with good thermal conductivity. Okay. It is a table of the typical properties of cast iron, so you can just look at it. Okay, we'll show this kind of a tensile stress and yielding stress and elongation with different types of cast iron. Okay. Okay, so this chapter will be ended here, and next one we're gonna jump into the area of electrical property of materials. Okay, see you next time.